So let's try to solve this one. So what we have here is an escalator, and this escalator is moving upward with an acceleration of 2 meters per second square in the orientation of the escalator. So let's consider this. Say we are having an escalator like this. So you know that there are going to be steps on which we will be standing. So this is escalator, and a person is standing on the escalator. Say he is standing at this particular point. And this escalator is moving with an acceleration a, which is equal to 2 meters per second square, and this acceleration is in the orientation of the escalator, and the escalator is making an angle of 30 degrees with the horizontal. So this is the information that is available within the question, and the weight of the man is given as 800 Newton. Okay, and the weight of the man is 800 Newton. So 800 Newton is a weight acting downward, and we know that the surface in contact, this particular point, the person is going to exert a reaction R, and we are asked to calculate the reaction when the current setup is as shown in the figure. So here, in the earlier cases of elevators, the acceleration was in the direction of the lift. So it was in the vertical direction. The weight, the reaction, the acceleration was all in the same direction, either upward or downward. But here it is in an inclined direction. So we should know that when the acceleration is 2 meters per second square in this orientation, it's going to have two components, one upward component and one horizontal component. So I can convert this acceleration into components like this. This will be a sine 30 and this will be a cos 30. Okay, so those are the two components of the acceleration. And once we have this setup, we are going to use the same condition, that is D'Alembert's principle. We know that D'Alembert's principle is sigma Fi is equal to MAI. So we need to have the direction I that we need to fix. So here I am fixing the direction I as, say, this direction. Okay, this is the direction. So net force, so R is in the upward direction, which is the direction what I assumed. 800 Newton is in the opposite direction, okay, acting downward. And then in the right hand side we have the mass. The mass is 800 Newton. So to convert it into mass, I am doing 9.81, okay, dividing it with 9.81 into the acceleration in the assumed direction, which is a sine 30. Now substituting the different values, we will get R minus 800 equal to 800 by 9.81 into 2 sine 30. So which gives R is equal to, this goes to the right side, so it becomes positive, 1 plus 2 sine 30 by 9.81. And if we calculate it, what we are going to get is 800 times 1 plus 2 sine 30 divided by 9.81. It is equal to 881.55 Newton. Okay, what we got is 881.55 when this is moving upward with an acceleration a equal to 2 meters per second square. So let's consider a similar case and let's calculate what is the value of the reaction if this lift was retarding at an acceleration, upward acceleration of, say, 2 meters per second square. There is two terms. One is acceleration, another one is retardation. Retardation basically means that a negative acceleration. Say if in the problem it is said that retardation of 2 meters per second square, it basically means that They are trying to tell that A is equal to minus 2 meter per second square. Okay, so let's see this case. If in the problem it was said that the escalator is moving upward with a retardation of 2 meter per second square. Okay, in such a case, the equation what we can write is sigma Fi is equal to MAI. We are going with the same condition. We are following the same sign convention, so we'll be getting R minus 800 is equal to mass is 800 by 9.81, and this component will be minus 2 sine 30, which means that R is equal to, I'm taking this 800 to the right side, 1 minus 2 sine 30 by 9.81, which will be, if we substitute it in calculator, we are going to get a value of 718.45 Newton. Okay, so in exam you can expect questions which talks about retardation. Whenever you see retardation, don't worry, it is just negative acceleration. Okay.